Okay, great. Hi, everyone. We are very happy to have Dr. Bubacarr Ba to have our 1W-MINDS seminar today. Dr. Ba now is an associate professor and head of data science at Medical Research Consult Unit, the Gamber at London School of Hygiene and Tropical Medicine. And he received his PhD in applied and computational math from University of Edinburgh. Dr. Ba has received many awards. For example, he was a Pan-African Scientific Research Council Fellow in 2021 and received Alexander von Humboldt Award at 2020. His research interests include AI, data science, machine learning, computer sensing, and so on. Today, he will talk about analysis of gradient descent for deep neural network learning. Dr. Ba, it's your turn.
Thank you very much, Longui, for that wonderful presentation. I don't know, this is generated by AI, I suppose. Let's see. Okay, so that will be the outlining. I wanted to talk about some work we have been doing for a while now around gradient descent. And this is joint work with my collaborators, Holger Raut, who is at LMU in Germany, and Ulrich Tristag, and Michael Westdickenberg, who is at our WTH Aachen. And this was mainly led by the PhD student, Gabin Maxim Ngunang, who is also at LMU with Holger. So yeah, I'm gonna go back to the outline. I'm gonna talk about, after the introduction, talk about gradient flow, gradient descent analysis, and then stochastic gradient descent. Most likely, I'll be a bit, I will spend more time on gradient flow and gradient descent, giving a bit more detail on that than the stochastic gradient descent, which is the ongoing work I just mentioned a while ago. And yeah, we just have simulation as proofs of concepts, and then I'll conclude. I hope everybody's hearing me correctly.
Yep,
so
you sound
yeah.
good.
Okay, cool. Well, I don't know. I think probably I'm preaching to the choir now. Everybody knows what AI and data science is and what's happening now, like autonomous driving. Well, I think this is a very old slide now. I should replace this with ChatGPT and things that are happening now with translation and languages. But also this, I wanted to keep it like, and right now I work for this institute that is a health research institute. We are very much interested in health, medical diagnosis, and other kind of related health issues. And AI also has a lot of potential in this space. In fact, I wanted to start to discuss a few things that I keep hearing when I go to these meetings now, where we don't have any differential or any equation written on any of the slides. Mostly people talking about health-related issues. But then, they are aware of AI and they thinking of using AI, but they ask some of these questions, that some of these questions are, in fact, one from a presentation by one who is leading AI and data science at the WHO. They have things like, okay, does the model function properly? Is it about hallucination, errors, biases, and accuracy? Does the model preserve autonomy and privacy? Doctors would want autonomy. You want to be able to take over at some point if you're not happy with what the model is doing. For instance, privacy is a big question. Can we trust the model? Is there a way we can interrogate to look at how transparent the model is, explainability, and other kinds of trust-related issues? And does it benefit, general benefit? People talk about issues around accessibility, affordability, who does it benefit? Is it more the commercial or the public, And then other social related issue closely related to benefit, like equity and other stuff, carbon footprint, the power consumption and things like that people raise issues about. And I wanted to say, well, can we formulate this problem in a more precise mathematical way so that we see whether maths can also give a solution to some of those problems, and try to formulate and say, okay, when you're talking about accuracy, errors, and hallucination, or is that the model is functioning properly, this generally you can think about generalization issues. And, people are working in mathematics to try to solve this problem. You want to understand the behavior of key algorithms like stochastic gradient descent, but then, approximation questions around neural networks might also help in solving generalization problems. Issues about robustness, these models also fail sometimes, show some kind of instability. Well, we have tools in mathematics where we try to understand stability and noise perturbations and so on, uncertainty around models, for instance. But trustworthy issues might be something around interpretability. People think about how do you replace a gigantic deep learning model with a simple explainable one. For instance, can we use maths tools to be able to show that there will be comparable performance, when you do things like that? Or, people are using physics-informed machine learning where you include constraints that respect the physics, for instance, and so on. And then, things like ethics and privacy, well, it goes down to what in terms of mathematical contributions to areas like encryption, or privacy-preserving technologies like differential privacy and so on. Yeah, I thought that there's a lot of space there for maths to contribute. Although we're doing a catch-up with engineering all the time, this is what happens. But it will be reassuring if we're able to explain some of these problems, we're able to give some satisfactory answers to these problems. And so gradient descent is one of those problems, as you can see. So then I'll just dive in deep straight. So we're talking about gradient descent for neural networks. I'm not sure. I think everybody here probably have heard about neural networks. These are some kind of organization of points that you would make what the brain does, or that's inspired by the brain, where you have neurons sending information to other neurons, right? And then they are organized in form of layers, right? And then we think of in a mathematical terms, this is just a function approximation. You have a function f that takes an input that's of dimension dx and then gives you an output of dimension dy. The input is the first, we would call it the first layer, and the output would be the last layer, and anything between that are considered the hidden layers. And it's just function concatenation. So this G would be the output of the layers. So Gn would be an output of the layer n. This is concatenated with, not concatenated, is composition of function. Is composed with another function G, the output of layer n minus 1, and this goes all the way down to the first layer G1. Okay, so you see that as composition of functions. So the G's are the layers, and they're always going from dimension d of j minus 1 to d of j, where d0 will be the dimension of your input and dn will be the dimension of your output. And G is typically an affine transformation. You will have a matrix multiplication to your input plus some bias vector. Okay, and this is passed through a nonlinear function, and we refer to as an activation function, which acts pointwise. So this problem actually, it's what falls generally, the problem we try to solve with these kinds of networks is a supervised learning problem, where you're given pairs of inputs, x and y's, m of them, and they each live in different space or could be the same space. And then you have parameter matrices, this is W's I saw earlier. And this neural network would output something that tried to approximate your outputs, right? The YKs. And the question is, how do you get this best XF that gets as close as possible to your Ys? And this turns out to be one of the way we solve this is through imperial risk minimization. What you want to do is you find the loss between what F outputs and your Y, and you want to minimize this in an average way. That's what empirical risk minimization gives us. And then there are many algorithms out there that people try to solve this, but the most practical out of those, and which is the most that's being used, of course, with different variations and adaptations, is the gradient descent algorithm, where you iterate, you initialize and iterate every new W or parameter vector or matrix is the previous parameter matrix minus some eta times the gradient, it's gradient descent as you know it, okay? And the etas are usually called the step size, and you can either fix that or you change them as you iterate also. So it's either adaptive step size or a fixed step size. And you would see some of the results also has this kind of flavor. So then, of course, if you want to force some of the problems that we looked at earlier, if you want to solve those problems, we want to be able to be sure to say, well, is our gradient descent converging to some kind of a minimum? Is it local or is it a global minimum? And all those have implications on the results that we will get if we use gradient descent. Okay, then I said we will look at linear neural networks, the results about linear neural networks. In that case, what we are thinking of is the nonlinear function that I saw, the activation function. It's just some constant or just the identity, if you want to think of it that way. So this will be just multiplying these matrices, and you to think of this a bigger matrix W, which is a product of all these factors. Okay, so it's what we are considering in this setting. Yeah, one would want to say, oh, this is trivial. We know this doesn't reflect what neural networks do, because the nonlinearity is crucial in making, we all know about the existence and uniqueness property theorem about neural networks that says you need at least 3 layers to able to approximate any function, but the nonlinearity is a must. So we need to have a nonlinearity for the function, for the neural network to be guaranteed to approximate some functions. So linear networks may not be as expressive for many applications, but then even doing gradient descent, analyzing gradient descent for these kinds of networks is non-trivial. This is a factorization. If some of us can remember or are aware that there's a whole area of matrix factorization that people work on. So it's a matrix factorization problem. You want to think of it that way, where this is an overparameterization of W, which means the rank is how to call it? It's a low rank in most of the case, and you can determine it in that way. So you want to just take the rank of the smallest, one of the smallest ranks among this product. That would be the rank of your W, for instance. Okay, so if our loss function is the L2 norm, you take those x's that I saw as inputs and stack them up as a matrix, and take your y's and stack them up, which are your labels or your outputs, and stack them up as a y matrix. You can rewrite your loss function in this way instead of doing, this is what I showed earlier in the matrix, in the Rex minimization thing. You can rewrite everything in matrix form, where the norm would be the Frobenius norm. So therefore, you can either have the L1, we call it, where you're looking at the product of all these matrices into one matrix, or you can have the Ln, where you are concerned about each of the factors, the behavior of that function based on each of the factors. So we would look at results in both flavors, looking at just W, what happens when you're looking at W, or when you're looking at these different factors. Yeah, one thing I wanted to point out is this Ln is not jointly convex on the W's on the factors. So one typical way that one of the method approaches to solving gradient descent has been to look at gradient flow. So we'll start with that, and we had some results in that area space also. So gradient descent, like I said, it's that, but you can think of the gradient flow as a continuous version of that, where you think of this tuple of W1 to Wn, which are functions of t, and then they would satisfy this differential equation. That would be gradient flow equation. So essentially, you can think of the gradient descent as a discretized version of your gradient flow, okay? And then, even the gradient flow, they're convergence questions. If we want to start there and see if we can prove something with gradient flow, and then maybe then you can move that and talk about gradient descent. But even gradient flow was non-trivial for this linear neural network setting. So there were a lot of series of works, probably I'll list in one of the slides later, but one of the earliest work in the space for linear neural networks using gradient flow was this work by, by Arora and his co-authors. And I wanted to stress this, he pointed out that if you have this condition which was called in their paper as the balanced condition, where you're looking at this product of the factors having this property where the j in the iterate j and j plus 1, this is what happens. If you have this condition satisfied and the gradient flow equation, then the dynamics of the parameterized weight matrix W is governed by this differential equation. And actually, this is for n is greater than 2. This dynamics is not easily tractable using standard Euclidean geometry. And this is what kind of motivates us to look in the direction of Riemannian geometry then. And let's set the stage for how the result came about. So we define a manifold in this case, which is a set of all matrices of dy by dx, matrices of rank k. So it is Colli mk would denote that. And we say, if you look at the right-hand side of the differential equation 1, let's consider this quantity here on the right-hand side. We can write it as a function of some function of v, which would be there in the tangent space of Colli m of k. And we denote that as a bar, and this actually we showed is self-adjoint and positive definite endomorphism. And its inverse also, we showed the inverse exists and it's self-adjoint and positive definite. And those are necessary tools for the proofs of the results. And then we propose for any W in MK, and when we have these vectors V1 and V2 in the tangent space, then the map GW, small gw of these two vectors can be computed this way. And it defines what we call a Riemannian matrix of class C, okay? C1, class C1. So we would define the Riemannian gradient flow for linear networks, which would be this. Therefore, you would have, you remember, instead of a nabla W here, we would have this small g, which is using the gradient matrix in this case, okay? So this nabla G L1 refers to the Riemannian gradient of L1 on MK with respect to this Riemannian matrix. Okay. Then we are able to show, based on this, that the convergence of the Riemannian gradient flow to critical points. And what we say, if we assume that X transpose, where X is the data, if you remember, these are your data inputs that you stuck into columns of A, you assume that the gram matrix is invertible. Then the gradient flow of W defined by that equation that we mentioned earlier, probably confusing you a bit with the arrow here. It's just the W here I'm talking about. The W, which is the product of the different Ws, W1 to Wn. So the flow is defined via this. The flow that is defined via this axis and is bounded for all t. And W finds some critical points of Ln asymptotically. That means as S tends to infinity, T tends to infinity. The earlier works, this was a major contribution compared to earlier works in a sense that there were stronger assumptions that existed in those results. For instance, in addition to assuming X and Y are full rank, they assume that also that you will always have M greater than the dimensions of the input and the output, okay? Which means that you will exclude setups where you have autoencoders, for instance, in neural networks. These autoencoders are just like bottlenecked neural networks where you have somewhere in the middle some layer that is smaller in dimension than the outer layers. Okay. So our further results, probably let me just remind you of the L's, how I define the L. The ln would be considering the factors, and the L1W will consider when you have multiplied out all those factors and you have W. So let's set R to be the minimum of those dimensions of the layers, okay? Then this tuple W1 to Wn is a critical point of Ln, to be a critical point of Ln, and we define W, that's just a repetition, and this is important, that the rank of W is less than or equal to R here, which is the dimension of the minimum dimension of your layers. Then we say W is a critical point of L restricted to M. And if we assume that W is a critical point of L1 restricted to Mk for some k less than R, then we can say there exists a tuple, W1 to Wn, where that product is your W, that is a critical point of Ln. Okay, so you would have the W1 to Wn, that tuple W1 to Wn, that will be critical point of Ln. Then the question is, to all those critical points, what are they? How do you categorize those critical points? So let's talk about strict saddle points, for instance. So we know about critical point either being saddle points or minima in that setting. So saddle points are problematic a bit. So we propose that L1 on A for k less than n, or less than the minimum of the dimension of n and k, satisfy this, what is called a strict saddle point property. Okay, what we mean is that all critical points of L1 on Mk, except for the global minimizers, are strictly saddle points. Okay, and then in the tuple, let the tuple to be critical points of Ln, such that we have this and rank k. If W is not a global minimum of L1, then these are strict saddle points of Ln. Okay, if the product is not a global minimum of L1, then you would conclude that the tuple will always be a strict saddle point. And we are able to show that the Riemannian gradient flow will avoid the strict saddle points. What do we say? We say denote this as a solution of the Riemann gradient flow with critical initial condition x naught. Suppose the solution that of 2 exists for all n and t in that, then this set of measure, or the measure of set of this of all initial points, such that the corresponding flow converges to a strict saddle point of L is 0. So we have a set of measures 0 for this to happen. This is probabilistically proven, and so with high probability, this is what is going to happen. Then we can say something now about converging to a global minimizer. So this theorem says that we assume this is full rank, and then we have an extra quantity Q, which is this product involving only the data, okay? Then you want R to be, R bar to be a minimum of the rank of this quantity here, and the rank of or the minimum of your dimension, sorry. When that happens, then you can say from all initializations, gradient flow converges to critical points of Ln such that this is happening, so that W star, which is the product of these tuples, is a global minimizer, or L1, on the manifold of matrices of fixed rank K for some K that is between 0 and R bar here, okay? And after all, we went further to show that if in the case that you have a 2-layer neural network, then from almost all initializations, this converges to a global minimizer of ln. And the question was, can these results be achieved for gradient descent? So that was the results for the gradient flow, and mostly the tools we use were like the two theorem. There's some results by Lower Savage. Mostly that was a key input to this. But then this was extended to gradient descent. But I'm gonna make a pause and see if there are any questions before I move on to the gradient descent now. Okay, how am I doing on time? Okay, let's go.
You're doing okay. You have like maybe half an hour if you want it.
Okay, cool. All right, no questions. So I move on now to gradient descent. So what we are saying is the gradient flow, the main key, one of the things that help us in the gradient flow was that it has nice properties like this invariance in its dynamics. We saw this this thing I call balanceness, where you say the product of matrices at iteration j plus 1 is equal to the product of the weight matrices at iteration j plus 2 j. Okay, here. This is the balanceness property. This is a nice thing about the gradient flow dynamics. This doesn't happen when you have gradient descent, but then gradient flow is far from being practical. You know, for practical usages, you need a gradient flow. You can think about a case where the step size goes to 0, right? This is not practical in our actual applications. So there was one important result actually that probably that I needed to share first before I talk about our results or other results. And this was the result by Aurora again in 1991 with some other co-authors. They had results, convergence of gradient descent for linear neural networks, but where they say they have what they call whitened data. If I didn't get it right, this is the definition. You say that X transpose is very close to the identity matrix. Okay, it's kind of a diagonal matrix. And they also used this. They came up with this new property instead of just saying balanceness, looking for balanced case where we saw that W transpose at j plus 1 times W transpose at j plus 1 is equal to W times W transpose. I think there's a typo. We should have a W transpose somewhere here. But what it is saying is that in this setting, you don't want equal. You may not have equality, but you can. If you're able to bound the difference by delta, you have what we call delta balanceness. Okay, and with delta balanceness, they could prove stuff. You know, they define this idea of a tangent matrix defined this way based on the data, and a constant C, which they call the deficiency margin. And they would want to bound the difference between the iterate or the W itself and this target matrix by the minimum eigenvalue of this target matrix minus this deficiency margin. And they say in their main results that assume that gradient descent is initialized such that the parameterized matrix W has what is called this margin deficiency with respect to the target matrix, and the weight matrices have a delta balance, have this delta balanceness property. Then on the appropriate constant step sizes, gradient descent converges to a global minimum. But they also showed in that paper that if you violate this deficiency margin condition, then convergence, you cannot prove convergence. And there were other results. Actually, this result is part of some of the results I'm going to mention here. But then there were other results on linear neural networks. Aurora is involved in a lot of them. This is what I've mentioned here. But then Chitur also has a nice paper which shows convergence to critical points. Jacob, Jibril, and Holga had convergence. Hongla, not Holga, had convergence to global minima for random initializations in the limit of infinitely wide layers. But the approach they used was what we call this neural tangent kernel. Okay, and then there was this work by Bach and Tizat that looked at convergence to minimizers for wide two-layer neural networks. But what we observed was the recurring idea was the convergence in function spaces containing neural networks rather than on the level of parameter spaces, which is what our work was focusing on more. Did I move too fast? Okay, yeah. And then if one looks at all these works that I have mentioned, there are certain limitations that are worth pointing out that actually we wanted to avoid in this work or wanted to improve upon in this work. So one is this Lipschitz gradient condition, which we find as a very strong condition and is typically wouldn't hold for neural networks. There's this strong conditions such as having this margin deficit margin condition in we saw in the last work. And of course, there are also some others that also focus on the initializations, which were very restrictive. There's work that actually didn't address deep neural networks, but looked at gradient descent in terms of simple linear regression. Most of the works didn't show that the gradient descent iterates are bounded, but they assume this, okay? And then it was difficult to see how you can extend some of the gradient flow results in these works to gradient descent. I just wanted to show that the strong descent condition has been used in some of the works earlier, and what it means is that you define strong descent condition as those two conditions, and the moment you have that, then you can use very old results from Apsil, Mahoney, and Andrew around 2005 that says that if you have a function mapping from Rn to R, which is an analytic cost function, then the sequence is xk satisfies the strong descent condition. If the sequence is satisfied the strong descent condition, then either you have the limit of this sequence goes to infinity, or there is a single point x star or x asterisk such that the limit converges to that point. So that's typically the tool that they would use, okay, for strong condition arguments. However, in our work, a key factor for the convergence of gradient descent has been establishing this boundedness of iterates. We didn't assume it, we wanted to establish boundedness of iterates. So here's a lemma that we begin with. We say, again, we always hold this condition that X transpose has full rank, and we say at initialization, the loss function with respect to an iterate k is always less than the loss function, the value of the loss at initialization. If that happens, then you can always say that the iterates are also bounded in this way, okay? The iterates are bounded in that way. We also made use of this balancedness condition. If you remember, this is how you define it. If you have that, then we can say that the iterates, the spectral norm of the iterate square can be bounded in this way, which is involves these delta balance constants. Okay, and then we are, based on this, able to derive bounds on certain quantities that we need in the analysis. Like you wanted to bound, of course, this is the delta balance that defined. We assume if this holds, but we're able to show that this would hold. And then based on that, you can bound the iterates, and you can even lower bound the difference in the loss function for different iterates. When we have that, we can show that actually gradient descent will converge to critical points of Ln if you choose the step size in a certain way, which is this way here. Okay, you have to have the step size chosen in this way, but it has to satisfy a certain condition where it's the summation of the iterates goes to infinity. Okay, and we are able to show actually these holds for the situation where you have a fixed constant, or if you have an adaptive a fixed step size or an adaptive step size. This depends on your iterates. And additionally, you can see that nk is of the order of 1 over n to the power 3, which is the number of layers to the power 3. So it's not a bad bound. But what kind of critical points do we convert? So this was a picture on a paper by Howley and co-authors where they tried to show the loss landscape of the ResNet 56. So you imagine how do you converge to a local minimum, or what kind of minimum do you converge to? So we did our critical points, but what kind of critical points? It was the question. And there was a results by Kwaguchi that proved that a local minimum of ln is automatically a global minimum, which is nice. So we want to use that and show that gradient descent converges to a global minimum. And this is just extending the result from the gradient flow work I showed earlier. And this has been published already in a paper by my co-authors. So we assume that eta k is a constant, or it is bounded below by c over k for some c greater than 0. And the limit of this goes to 0. Then the following would hold. For all initializations of your weight matrices, gradient converges to a critical point W of Ln such that the W is a global minimum of L1 on the manifold of matrices of rank K. Okay, and actually again following the results in the gradient flow, you can say for the case where n equals 2, gradient descent also converges to a global minimum of Ln for almost all initialization. Remember these definitions of Ln and L1 again. All right, I was not going to transition to stochastic gradient descent. Any question? All right, I'll move on then. Stochastic gradient descent, very similar, but what we want to do is we want to do updates in a way that we don't consider all our data, okay? So we consider when we compute this gradient, we just pick data points that are indexed by this set K here, set S sub K, okay? This could be, like I said, this could be any subset of M, 1 to M, and even 1 in the case, and the 1 is the extreme one. I think that's what we usually would call stochastic gradient descent, where you're just picking one data point at a time. But then you can take a couple at a time. This is mini batch gradient descent, for instance. You can take different batches, okay? But also the results depended on having a regularized loss. So instead of the ln that we saw earlier here that was defined in the previous slide, previous, that one here, that was ln, right? Instead of that, we add a regularizing term here, okay, RW, which is defined in this way, okay? So there's some lambda times 1 over 2 of the iterates, the parameter matrix to the power some beta, where both beta and lambda are some quantities greater or equal to 0, respectively. So we are able to prove something when we have this regularized loss. It was a challenge to prove something without the regularization term, something in the flavor of the results we have, gradient descent. But with this, we're able to show something. I'm not going to go a lot more detail into this, but one of the tools that was helpful is this asymptotic pseudo trajectory, okay? And because it helps us to define an interpolated process, and this interpolated process helps us to show some convergence, okay? And I don't know if I should bore you. So we define an asymptotic pseudo trajectory in this way. You have M and D being a matrix space, an asymptotic pseudo directory for some function psi is a continuous function mapping R to M that satisfy this condition for all t, and j going from 1 to n. So remember, we typically would define it, if you have a flow, we define this phi as our flow that is mapping this space to M, and then we can define, we can initialize our flow in this way, and we could say this about the composition of two flows. This is an extra condition that we need. If we define tau as this summation of our step sizes, we can introduce an interpolated process in this way. X of t would be xk plus this interpolation here. All right. So there are common assumptions, like I mentioned earlier, but what kind of tools that people use to prove convergence of gradient descent or gradient flow? Similarly, for stochastic gradient descent, there's something like the L smoothness property, where you, very similar almost to our Lipschitz constant thing. You have this property that holds, or you can say you have a property of the variance, bounded variance, for instance. If you assume that holds, then you're able to show something. If you assume the expected strong growth, which is this quantity, this also holds. This also helps you prove something about convergence of gradient descent. But ours, again, like going in the direction of gradient descent, our main ingredient was, again, establishing boundedness of the stochastic gradient iterates. And because we're using it, some results that depends on this asymptotic pseudo trajectory, which you can talk about convergence either in terms of the boundedness of the stochastic process or the L smoothness of the function. So we were using this force property here in the proof. And so for boundedness, we can say that under some mild conditions regarding the regularization term in our regularized laws, and these conditions on our step size, we want to say all the time the sum of the step size diverges, but the square of the step size, square of the step size would converge or is bounded, okay? Then we say we can show that the iterates of stochastic gradient descent are bounded almost surely. And this then uses, with that, we are able to use the results, very old results by Benaim, that shows that if M is smooth, CR, a Riemannian manifold of dimension M, and V maps M to R is a CR map. F, the gradient vector of the field, is defined this way, and we assume that F induces a global flow, P, and X is a pre-compact assumption pseudo trajectory of phi. Then we say the L of X consists of equilibria, okay? And V of X converges as T goes to infinity. At least we were able to say that SG converges to this equilibrium, which we would call as critical set, almost surely. And the regularized laws applied to the stochastic gradient also converges almost surely based on these results from Benaim when we prove boundedness. We had simulations. The first work on gradient flow, we had some simulations that shows like a proof of concept, like we looked at, for instance, here, N here is the number of layers. We looked at, we made simulations for situations where we have a two-layer neural network, a 5-layer neural network, a 10-layer, and a 20-layer neural network in some instances. And we see how it converges as you iterate through. And we measure, like from here, like the difference, the convergence, it is different between the current T and the final T, for instance, of the iterates, but also we measure the difference between this quantity Q, if you remember, that I showed in our force theorem, that it's also like a pseudo, like some kind of matrix that's that we can converge to, for instance. So you see, we saw some convergence with the gradient flow. In this situation of gradient descent, again, we need to choose a step size. In this case, we had a bound on the step size. We take, let's say we started with a smaller step size, like 10 to the power minus 5, which satisfied this condition. We looked at 10 to the power minus 3, which also satisfied this condition. And by the time we got to 10 to the power minus 2, which is 0.05 in the last one here, we have violated this rule, and you can see we don't have convergence, we have divergence instead. Okay, but nice thing is, as you increase, before you get to the violation of the rule, as you increase your step size, you see that you're converging faster, which is typical of gradient descent. All right, I will wrap up by saying that we were aware of restrictions around the earlier results that preceded our results around gradient descent, and one of those is the strong assumptions like assuming Lipschitz gradient and boundaries of gradient assumption, dimension constraints where you don't want to have things like autoencoders, for instance. There's some assumptions about initializations, and there's some of the work was done on similar but not quite the same problem, like looking at linear regression compared to the deep neural network, for instance. They're not quite the same. And we have this convergent result of stochastic gradient descent, which was initial result, which was restricted only to this case where you have the expected value of the gradient going to 0. And we improve the state of the art by first showing some results about gradient descent converging to a global minimizer when we consider gradient Riemannian flows. But then we looked at the convergence of gradient descent, where we have to respect the bound on the step size. We show that it converges to some critical points of L. We saw some global convergence, which mimic an extension of the gradient flow. And we were recently able to establish the boundedness of stochastic gradient descent iterates, which was helpful to show that stochastic gradient descent will at least converge to a critical set. We are not able to show that this critical set will be convergent to critical set leads to a convergence to a global minimum. This is one ongoing work for now. And thank you for listening, and any questions.